least for now. All right, so welcome everyone to the very last parallel session of the week. So in this session, we have 4 speakers. For each of them, we will have a total of 20 minutes, splitting into 15-minute talk, 3-minute questions, and then 2-minute transition time. And especially because the talk time is rather short, it's probably best to have questions after the talk rather than during the talk. And alternatively, if anyone leaves a question in the chat box, then the speaker could provide an answer at his or her convenient time, either during or after the talk. And I guess that's it for the introduction. So with that intro, let me introduce our first speaker. The first speaker of the session is Kang-Sin Choi from Ewha Women's University. He will be telling us about aligned natural inflation in string theory. So please go ahead.
Thank you. Good afternoon and nice to see you. So I would like to talk about embedding aligned natural inflation in string theory and also try to extract some observable by stabilizing using a large volume scenario. So this work is done in collaboration with Stephen Angus and Jang-Seop Shin. So the idea of natural inflation is to identify axion as inflaton. So the merit is the shift symmetry of axion protects the potential from quantum correction. So this can be free of eta problem. And the height of this potential is given by power spectrum of scalar perturbation. And the width or the decay constant is constrained by the scale invariant factor or spectral index. So if we compare this to spectral index, then it requires that at least it needs to be greater than some number of Planck scale. And this immediately gives rise to some problem. So if we try to embed this directly in string theory, then string theory cannot allow this unnaturally large scale. And also there is some problems in effective field theory description. And also we will face some problem related to global symmetry that is believed to be violated in quantum gravity. So one good way to evade this problem is suggested by Kim Nillet's fellows, and this is known as KNP alignment. So if we have some multiple axions, then some alignment makes one of the components to be flat enough. For example, if we have 2 axions here, if we have some alignment of charge like this, then you may see easily that these 2 arguments becomes the same. That means that the orthogonal combination becomes flat. So if we allow some slightly small misalignment, then we can lift that flat direction, and the resulting effective decay constant can be enhanced by this alignment factor. And we can see that the other axion becomes heavy and decoupled. So this is a good way to effectively enhance the decay constant. So note that this is purely given by the charge relation. So we can separate this alignment condition from the kinetic term. And what is the origin of these axions from string theory? So in string theory, we have some various antisymmetric tensor field, and performing dimensional reduction, we naturally have axion. And in supersymmetry, this is naturally paired with some dilaton. And in world volume theory of string theory, this dilaton is also the volume moduli. So expectation value of this becomes volume. And this gauge symmetry in this antisymmetric tensor field becomes some shift symmetry of the axion, and that is further broken to discrete symmetry if we wrap some d-branes on the internal cycles. And we can see that the spur potential obeying this symmetry is given like this. So exactly the same form. So if we have some scalar potential, then we have exactly the same scalar potential. And the supersymmetry is also very restrictive enough that actually this instanton vector is also given from this, because instanton is basically the size, and yeah, it should have the same relation. Okay, so let's go to the kinetic term. So kinetic term information, this contains some information in the internal geometry, because the scalar potential is given by logarithm of internal volume. So scalar matrix obtained by the scalar potential. And the axion decay constants are the eigenvalues of them. So usually we think of some diagonalized eigenvalue, but here, even if it is non-diagonal, we can deal with alignment mechanism and some weak gravity conjecture description later. So we define axion decay constant as matrix valued 1, like this. So yeah, because the axion comes from the dimensional reduction. So if we have some number of cycles, then we have as many axions. And it is very natural to have multi-axions, because in general, there are many 4 cycles. So we take some particular example by this geometry. The volume is described by this. So it is easy to see that if we have this dependence of the volume, then this scalar matrix determines the axion decay constant as one of this volume moduli. So this is measured in string unit. However, the axion decay constant is given by the multiple of Planck scale, and because this is valid, because 1 of tau is expansion parameter. So we should have tau greater than 1. And this shows that we should have axion decay constant that should be sub-Planckian. So this is the natural value. And we combine these two moduli stabilization. So the idea of large volume scenario is, so basically it's easy, relatively easy to fix the complex structure moduli by turning on flux. However, string theory and its derived theory has so-called no-scale structure. So scalar moduli remains unfixed. And if we turn on some source violating this no-scale structure, like some next leading order correction to the volume given by basically the Euler number, and then also we can consider some non-perturbative superpotential we have seen just before. And this is dominated by small cycle because there is less suppression. So these two compete, and as a result of normalization, minimization, we fix volume in terms of size of the small cycle. So this will fix the size of the entire manifold. However, the large cycles remain unfixed. By the way, the axions associated with the small cycles cannot be used as axion taking part of alignment because they are decoupled. And still, we have some bulk axion, which is large axion, describing this bulk geometry. And if we turn on some one-loop correction given by some Kaluza line and winding contribution, then we can stabilize the moduli. And this time, because the overall scale is fixed in the first step, so we can fix the relative size of the moduli in terms of this one-loop correction. And the challenge is so far only the moduli stabilization is done for some simple cycle, and if we introduce some complicated cycle, then one-loop correction becomes very complicated. So this is one interesting challenge. Okay, so we have obtained axion potential from actually gauge-no condensation on D7 brane, and there is another interesting enhancement effect from the rank of this strongly coupled gauge group, because this is divided by n. So this effectively rescale the charge by 1 over n. Then, as a result, we have enhancement of the effective decay constant by this n factor. But there is some price to pay, because even if we have this enlarged decay constant, actually we have also n branches of this vacuum parameterized by different phases of this Gaussian condensate. And when inflaton rose, then it is also possible to tunnel to another branch. Then this effectively cancels this n enhancement factor. So we should make sure that there should be no such tunneling. So we can calculate that this tunneling amplitude and this exponent bubble action is scaling like 1 over n. So this sets some upper bound of this n, and for a reasonable choice of parameters, we may show that this cannot be larger than some number like this. And in string theory, actually these n's are typically smaller than this. And there are also many other alignment mechanisms. Okay, so another obstacle for alignment is actually weak gravity conjecture, stating that gravity should be the weakest force in any consistent theory of quantum gravity. And this is some quantification of the statement that the consistent quantum gravity violate global symmetry. So if we consider some Yuan gauge theory, then by considering the decay of extremal black hole, we can show that the electric charge should be larger than mass, and this is another expression of that. So because this Yuan gauge theory is described by vector field sourced by some point particle, we may consider some axion system as some force described by scalar sourced by instanton. But there is some tricky point, because if we extend this to some higher dimensional or lower dimensional object, then this becomes trivial. However, this becomes again non-trivial if we consider some dilaton dependence. So we can take analogy and consider that the axion force should be stronger than gravitational force. But there is some tricky point of this normalization, and also this, if we have more than, this relation comes from the decay of this extremal black hole. So the question is also, what is the extremal object for the axion? There is also a challenge if we have multiple axions. So not only individual axions satisfy that weak gravity conjecture bound, but we should have some stronger bound, because there is some conservation of charge and so on. So with the help of the supersymmetry, we can fix actually action and the decay constant in this way. So this is very restrictive. So if we plug this again to this ratio vector, then we obtain this. And this is actually given by the ratios of charges. And okay, so if we plot these vectors varying these charges and this Keller moduli, then they are along the same line. So this can be regarded as some tangent line to this circle, and this actually fixes the circle. And we can show that this is the inverse, square root of inverse of the sum of these powers, which is nothing but the complex dimension divided by 2. And the extremal object is actually, there is some gravitational solutions to this axion instanton system, namely Giddings-Strominger wormhole. And if we include dilaton, you can show that the extremal charge is exactly the same as this radius. So we apply this to this weak gravity conjecture. Then these aligned two axions are located almost the same point. So we need some another instanton. And the condition for this being located at the opposite part of the circle, that that gives some bound like this. And actually, if we consider the Keller-Kohn condition, the existence of the Calabi-Yau manifold, and also the power spectrum constraint, then actually they are limited in very small, narrow range. So it is very interesting. So most of the cases, this is toward isometric geometry. So if we make some statistical analysis, then also it favors some isotropic geometry. And although alignment is very easy, effectively large decay constant is relatively difficult. However, this is possible in string landscape. So this is the last plot. So after moduli stabilization, we can obtain some concrete values, and we can plot like this. So we can vary this rank of gauge group and charges and this moduli, and they are overlapping and they are along the same strip because actually this natural inflation is described by just one single parameter. Okay, so yeah, I have embedded natural inflation in string theory and moduli stabilization. We can concretely obtain the this number, so we can compare those with those in cosmology. So KMP alignment and weak gravity conjecture is considered, and we have refined those conditions, and we could fix, clarify the relation. Okay, that's it. Thank you for the attention.
Thank you very much. Thank you for the nice talk. So are there any questions from the audience?
Maybe I can ask a question.
Oh, please.
Hi. Can you show some of the convex hull plots again? Like that one, for example.
Yeah, I have two plots. One is this, and the other is this.
Yeah, I'm a little bit confused by these plots.
Mm-hmm.
The first, the unit circle.
Yeah.
What does it represent?
Yeah. So weak gravity conjecture states that the axion charge should be greater than some number given by gravity. So being outside the circle means this charge is greater than this. So for individual axion, this is satisfying weak gravity conjecture if this lies outside the circle.
But I'm very confused. And the blue dots are the instantons you actually compute.
Right.
Or
so whatever number we put, yeah.
I'm confused. The black circles should be the extremal instantons, so to say.
Right.
And you're saying that you are obtaining in supergravity with supersymmetry exact solutions that are exactly super extremal. That's strange. When you compute in string theory instantons like deep range wrapping circles, you typically get extremal objects whose charge is equals to its mass. But here you seem to be getting something that is very super extremal. That's something you don't typically know how to compute in string theory.
Yeah, maybe I confusingly used the terminology extremal. So yeah, as you said, maybe that extremality in string theory means maybe this jet vector
on the line.
Yeah. So maybe extremality from black hole-like thing. Yeah, I mean by this. So this can be away from this.
I see. And can you show the next plot?
Yeah.
Maybe the next. Because I would say that the blue dots should lie on the extremal surface, which is what the convex hull should contain.
Yeah, you are right. So I missed one thing. So all the instantons are lying on here, but if we consider some anti-instanton, then actually this is minus of this. So they are all along this line. So we should include the anti-instanton at the same time, and with them, all of the convex hull made by all of them should contain this circle. So yeah, actually. Yeah, there are two lines.
Yeah, that's the statement I don't understand. The should contain the circle. The circle in this context is not. I don't see its meaning. What they should contain is all the sub-extremal objects. But if the extremal objects are the blue dots, what it should contain is just what is inside the green contour. So
Yeah.
I'm a bit confused about the black circle.
Right. So maybe by your extremality, everything lies on everything. I mean,
Right.
every instanton lies here, and every anti-instanton lies here. So yeah, so it is not clear what is the non-extremal. Yeah, maybe.
Yeah, for instanton is very confusing.
Yeah. Maybe some different values of dilaton makes this Wormhole solution non-extremal. Yeah. Maybe that will fill. Yeah.
That's a very confusing aspect. Yeah, indeed. Thank you.
Yeah, thank you.
So yeah, the time is almost up, but if there is maybe one urgent question, we can take it. Otherwise, let's thank Kangxin once again for the nice talk.
Thank you very much.
Thank you. And let's move to the second talk. The second speaker is Viraf Mehta from University of Göttingen. Could you start sharing your screen, Viraf?
Yeah, sure.
Okay.
Full screen. Okay.
Great.
Can you see it?
Yes, we can see it.
Great.
So Viraf will be telling us about landscape exploration with black holes. So Viraf.
Thanks a lot. Thanks a lot to the organizers for giving me the opportunity to present some recent work that I completed with Dottie Marsh here in Göttingen and Liam's group at Cornell. And so, as Sungju said, this will be a look at exploring the string theory landscape using black holes. And actually, our work takes this unprecedented step toward constraining a large ensemble of string theory backgrounds. So most of the geometric construction details were actually given by Liam on Tuesday. But what I'll do is I'll just briefly review them here for completeness sake. So I'll do this in the first part and then discussing exactly which portion of the Axioverse that I'll be talking about, namely the type 2b or the Kreutzer-Skarke Axioverse. And then I'll go on to discuss what physics we use in order to constrain these systems, which will be black hole superradiance.
Viraf, are you actually turning to the next pages? Because it's still the, sorry.
No.
Okay, work? You didn't. Okay, I'm sorry.
Yeah.
I'm sorry.
No, it's fine. I was also, sorry. Okay. So this is our axion Lagrangian. The Kreutzer-Skarke Axioverse derives the input for this Lagrangian directly from compactifications arising in the Kreutzer-Skarke database, which is a database of essentially topological quantities. This is currently our largest source of Calabi-Yau threefolds. Until very recently, computing these quantities, especially in the larger string geometries, was actually very difficult or impossible due to the long computation times and the intensive computations involved. However, advances in both technology and methodology have allowed us to actually derive axion statistics now, even for the largest geometries in the Kreutzer-Skarke database, that is, with systems with up to 491 axions. So the question is, how do we derive the inputs, or where do the inputs for our axion Lagrangian originate in terms of their geometric quantities, namely those that are circled here? So first, I just want to note that actually we're going to ignore the phase inside the cosine term, not only because we don't know what form it takes or how to calculate it, but but we actually do include it in our paper. So if you want details about how it affects the axion statistics, then I highly recommend you take a look at our appendix in the longer paper from March. Okay, so what we're doing is compactifying type 2b string theory on some orientifolded Calabi-Yau threefolds. So in a given one of these backgrounds, the close string moduli, as detailed in the previous talk, there are H21 close complex structure moduli, the axial dilaton, and then there are H11 of the Kähler moduli. So what we can do is fix the complex structure moduli and the axial dilaton completely by some suitable flux choice, while, of course, the Kähler moduli will remain unfixed to all orders in perturbation theory due to the gauge symmetry of our C4 form, the Ramond-Ramond 4 form, which in some basis of divisors, these Ds, actually define our axion basis. And because our axions derive directly from the Kähler moduli, there are H11 axions in each of our systems, each of our geometries. So with the overall volume of the Calabi-Yau threefold that we can derive from the triple intersection numbers, and then the volumes of curves, what we can do is then just easily compute the Kähler metric, or the Kähler potential, and then derive the Kähler metric, which serves as the kinetic matrix in our axion basis. So at this stage, our axions are all shift symmetric to all orders, and these are only broken then by some non-perturbative effects, such as previously detailed, branes wrapping 4 cycles, or maybe some gauge-Eno condensation. So for instance, in our case, we take Euclidean D3 branes wrapping the 4 cycles, and these will give a superpotential contribution with some associated charge, which are these Qs here. Our index A on the Q will run over the number of effective instantons, that is, those derived from prime effective divisors. And this is some finite number P. And so Q, the capital Q, is some rectangular instanton charge matrix with dimensions P by H11. And so once Q and K are fixed, lambda can be easily computed. And in fact, these quantities can now be computed extremely quickly using the software package from Liam's group that he detailed on Tuesday called CY Tools. So let me just mention here that our results were obtained at 3 different points in the Kähler moduli space, indicated here by these 3 stars. So this is just a cartoon for the H11 equals 2 case, that is just 2 directions. And I've presented here the different Kähler cones, which I'll just briefly outline now. So it's worth mentioning here that, of course, we currently can't compute the Kähler cone for a Calabi-Yau threefold, especially for a large ensemble of geometries like the one that we studied. But as Leah mentioned, this could well be possible in the very near future. What we can do is compute the Kähler cone of the ambient variety, i.e. the triangulation, the fine regular star triangulation that we obtain using CY tools. So this here would be the dark blue area. We need to ensure that, of course, we're in a regime where we have some computational control over the alpha prime expansion, namely with some small string coupling. The proxy for this, in our case, is just the size of the Kähler form, this J. And so if we restrict this to have some minimal value, let's say 1 in string units, this allows us to actually approximate the region in which we have control over the world sheet instanton corrections, which is the proxy for this alpha, for control over the alpha prime expansion. And this is given by the red region here and is known as the stretched Kähler cone. So the red star is then just at the tip of this stretched Kähler cone, which is just the point closest to the origin. So we also know that each of our triangulations that we obtain using CY tools doesn't necessarily uniquely describe a single Calabi-Yau threefold. And so what we can do is actually glue several of the Kähler cones obtained from the ambient varieties together. So this would be the light blue region. And then, of course, we do the same restriction of J, the Kähler form size, and then obtain the stretch Kähler cone for the union of several of these Kähler cones. And so the tip of which is just indicated by the gold star. Finally, there's some limit in our Kähler moduli space at which we can attach a stack of D-branes that would describe the standard model and produce some QCD-like axion. This is the gray star and is much further inside the red stretch Kähler cone. It's far enough from the walls such that the minimal device volume is 25, which would then reproduce a realistic gut coupling. Okay, so now that we have the tools in place in order to find our axion spectra, the question is there a way without specifying conditions for the standard model or a particular cosmological history to constrain these systems of axions? So there are a few different effects that one could study. However, what we're going to focus on today is black hole superradiance. The phenomenon of superradiance from rotational bodies is a general feature which can occur with systems that present a dissipating surface with a non-vanishing angular momentum component. So Penrose first postulated this for a spinning black hole. To an outside observer, the black hole has a region just outside of its event horizon, this ergo region, which is demarcated by the orange boundary, inside which the inertial frame dragging is so fast that actually normal matter probes cannot remain at rest, namely that the time translation killing vectors become space-like. So if a bosonic field enters this region, the killing energy density then can become negative, and our observer sees a growth of the bosonic field as an extraction of angular momentum from the black hole. And this is known as the superradiant instability. So we know that in such a system, the Klein-Gordon equation possesses bound states with complex eigenvalues. And these would be then hydrogenic in nature, i.e. what we're forming is some kind of gravitational atom. The fine structure constant of this gravitational atom then determines the efficiency of the instability, the superradiant instability. And this is dependent then only on the scales in the problem. The Schwarzschild radius of the black hole, which is just proportional to its mass, and the Compton wavelength of the bosonic field, which is also proportional to its mass. So when these are comparable, superradiance is maximal and runs until the superradiance condition is no longer satisfied, or until the self-interactions of the bosonic field quench the instability. So what we can do then is just map spin-down exclusions from the astrophysical measurements of black hole masses and spins to the axion mass and decay constant plane. And that's what I've done here. So in our analysis, we actually consider 15 stellar mass black holes, which are these ones in the kind of reddy orangey colors on the right, and 10 supermassive black holes, including the latest results from Messier 87, which is the one on the far left. The excluded axion masses actually fall into these three windows. And what we also notice is that self-interactions put bounds on the decay constants. So axions with decay constants below around 10 to the 12 GeV or so cannot form the cloud, and so would not spin down a black hole. So the question is, when we derive our axion spectra, do they actually hit these exclusion windows? Well, first let's look at the decay constants, which we can just derive by computing the diagonal components of the quartic self-interactions. Just F squared is m squared over lambda. But I won't present lambda here. It's obviously much nicer to see the decay constants, because this is what we see more often. And what we can see here is that F decreases as H11 grows. Although what's nice is that the black hole superradiance constraints seem to remain valid up to quite large H11, which means that we, in principle, can actually impose constraints on very many geometries. In red, I've indicated the peak of the exclusion plot that I'll show in a second, which is at around 157, H11 equals 157. In fact, the decay constants will shut off the black hole superradiance constraints completely at around H11 equals 300. What's also interesting here is that, almost as expected, the decay and has been written about previously in the literature, is that the decay constants are actually log normally distributed. The discrepancies that you may see are actually just because of poor statistics rather than actually not following some log normal distribution. What we can then do is look at the masses. First, we notice that from the scale on the left, the massive axion spectrum only makes up a very small part of the overall spectrum. And in fact, we found that over 70% of axions in our geometries are massless, that is below the Hubble scale. We also see that there are axions in the black hole superradiance exclusion windows at all H11s. And thus, until the decay constants shut off the black hole, prevent the condensate from forming, we can get some constraints. So we put everything together and ask, do black holes actually exclude string geometries? And in fact, yes. What we can do is actually exclude at all 3 points in the Kähler moduli space significant portions of the string axiverse for the very first time. Interesting things to note here are, for instance, that the union of stretched Kähler cones tracks the single stretched Kähler cone data, which is the orange line compared to the red line, with some increased shift. This is to be expected as the tip is actually closer to the origin and thus contains more curve volumes close to the condition of J is similar to 1 or equal to 1. Following the same arguments, of course, the point very far inside the stretched Kähler cone has more instantons contributing from much larger volumes, and so both the masses and the decay constants are actually shifted quite dramatically to lower values. And F shuts off black hole superradiance in this case at around H11 equals 100. So I just want to emphasize here that we're not presenting a realistic model of the universe, only that there are geometries that are excluded due to black hole superradiance. These we expect would serve as a conservative estimate, as of course Saxion dynamics, namely Kähler moduli stabilization, would play a role. So for those interested in more details, please look at our paper, which was recently accepted at JCAP. Okay, thanks a lot for your attention.
Thank you very much for your nice talk. So question time. Are there questions from the audience?
If maybe I can ask a question.
Of course, please.
So you have these setups with very large numbers of axions, and you consider very different combinations of instanton effects that stabilize them. Can you see also enhancements in the effective decay constant? Do you get close to effective decay constants that get close to M Planck? Because you should see all these type of inflation enhancement or alignments, or maybe your analysis does not cover.
Yeah, indeed. So the now that we have this this large database of axion spectra, this is one thing that we're actually currently looking at, because indeed the difference here, just to emphasize, is that we don't use the kinetic eigenvalues as our decay constants. We really compute the quartic self-interaction and then derive the decay constant from there, because this would in principle be more akin to the physical decay constant of the axion. But indeed, you're right that in this basis, it's likely that we would have some kind of alignment and perhaps approach some kind of, though we don't have a Transplanckian decay constants, it for sure we probably have some alignment that gives us a very large effective decay constant. Yeah.
Right. So your proxy for the decay constant that you derive from the quartic coupling should also be, should be a good approximation to maybe other definitions of the decay constants, but you don't get close to. How close do you get to the? You showed a plot, I think it was, but how close do you get to M Planck?
Right, right. Indeed, the smaller geometries correspond to larger decay constants, and indeed contain decay constants around the Planck scale. Sorry, go on.
The ones with larger decay constants are the ones with actually less number of axions.
Exactly.
That's surprising.
It's not so surprising, because if you think of so if you look at this plot, for instance, as I take more and more Kähler moduli, what actually happens is as H11 increases, the stretch Kähler cone, this red region, let's take just a single Kähler cone, this red region, actually the walls become more and more parallel, and the red star would then move further and further into the Kähler cone. So it would move further away from the origin, and therefore the kind of minimal volumes that contribute to the masses. There are fewer volumes that are of order,
right.
Kähler forms of order 1.
Right. So in some sense, string theory is preventing this enhancements of the effective decay constant by multiplying the number of axions.
I won't make that statement, but it's a fair enough conclusion, maybe. Yeah.
Okay, good. Thank you.
Okay. So are there any further quick questions? If not, let's thank Vera again for the nice talk.
Thanks a lot.
And then let's move to the third speaker. Nicole, could you try sharing?
Yes. Okay. So let me start from the beginning. Can you see my screen?
Yes. And could you try turning to the next page?
Okay.
Okay, it works.
It works. Okay. So thank you. Sorry.
Yes. Okay. Yeah. Let me briefly introduce. The next speaker is Nicole Riggi from DESY. She'll be telling us about fuzzy dark matter from strings. Please.
Yes. So thank you very much for the opportunity to present this work that I did in collaboration with Michele Ciccoli, Veronica Guidetti, Arthur Rebecker, and my supervisor, Alexander Vespa. And so this work is not published yet, but we are very close to put it on the archive. And this work, the main focus of this work is to study the ultralight axion coming from string, how they behave when we relate them to the bound, to the experiments and the bounds that they put on the various values of the axions. And today I will focus on how these string axions behave when we take them to be fuzzy dark matter candidates. So so fuzzy dark matter, with fuzzy dark matter, we mean that we take the dark matter to be made of ultralight particles, and this was a proposal coming back from the beginning of the millennium, and the proposal was made to solve some problems that the normal lambda CDM models was showing. And then it was proposed that this kind of particles can be actually ultralight axions. And so it was proposed that this axion should have a mass which should be around 10 to the minus 22 electron volt and a decay constant around 10 to the 16 GeV. And so, as you can infer, the fact that the decay constant is so high can be seen as a possible sign of the string axiverse, because when we go to such a high decay constant, then we should take into account also the effects of quantum gravity. However, as was pointed out in this verse, there is a clash with the weak gravity conjecture, because if we consider the action that gives this mass and we multiply it by this decay constant, then we can see that this product is actually slightly bigger than the Planck mass. So this can be seen not maybe as a proper violation of the weak gravity conjecture, but better the fact that this product is highly sensitive to the extremality bounds that enter the weak gravity conjecture. So it's also interesting studying fuzzy dark matter from this point of view, because it can give more insights also on the quantum gravity. And okay, so we study fuzzy dark matter, as I said, as string axions. So first, because this high decay constant that they should carry, but also because it was pointed out in some works that fuzzy dark matter, a halo of fuzzy dark matter can be actually made of many ultralight axions. So fuzzy dark matter can have a multiple nature. And therefore, as it's well known, when we compactify string theory from 10D to 4D, then we have a plenitude of axion arising in our 4D effective theory. And also these axioms can acquire slightly different masses depending on how we give them a potential. So we can give a potential to this axiom from, for example, instantons engaging in condensation and brains wrapping cycles, and so on. So all of this said, we would like to point out in this work that it is not so straightforward to have these ultralight axioms with the right properties. And so we decided to investigate what should be our 4D effective theory and how, what values of the Calabi-Yau and so on can give rise to a mass and a decay constant which represent fuzzy dark matter. So this is the 4D effective theory that you get when you compactify from 10 dimension to 4D to a 4D theory. And this is the usual scaling of the mass of the axiom when you start from a 10D theory. So as you can see, it scales as the exponent of the action. And this is the equation that gives you the fuzzy dark matter abundance as a function of the mass of the axiom and the decay constant. And this is the initial value of our axionic fields. This should be considered, should be evaluated as happening before inflation, because for a decay constant of 10 to the 16 GeV, then obviously this axiom is gets a mass before the inflationary epoch. And we, as a first approximation, we consider it to be decoupled from the inflationary dynamic and just as a spectator. So we consider the type to be string axivers. And in particular, we consider closed string axioms because open string axioms are more model dependent. And these are all the type of axiom that you can have. So you can have many of these, all of these axioms. But as I showed you, we want something that saturates the weak gravity conjecture bounds, or also is slightly bigger than the Planck mass. So therefore, what we focus on in this work is are as candidates the C4 axiom and the C2 axiom when realized as after axiom. So let me explain you this table. We take the C4 in two different scenarios. So when we have only one C4 axiom or two C4 axioms, and this is a rough estimate of their S times F value. And to stabilize this axiom, we have to use the large volume scenario. And in this way, we can reach very, very low masses. And also we focus on this new class of axioms that live in a workload throat of the Calabi-Yau. And we have this, their S times F that depends on the flux ratio. So we have fluxes and we have a ratio of their flux numbers. And then on the volume of the Calabi-Yau and on the volume when the throats marginally fit the Calabi-Yau. So we start, let me start from a simple parametrization of Calabi-Yau, which is commonly used in the literature, which is called the Swiss cheese Calabi-Yau. And when we take the large volume scenario, then this volume can be parameterized by a single modulus that should be bigger than all the others. And here we have the axiom, the action of our axiom, where n is the number of brains that we use to create a potential for this axiom. And then we have the decay constant and the mass. As you can see, the mass is scaled as the action. And this is our findings. So here I'm plotting the mass of the axiom as a function of the dark matter abundance, and the decay constant of the axiom as a function again of the dark matter abundance. And here we vary the number of brains, and also this C min and C max, which contains the free parameter of the underlying quantum gravity theory. But we take a range of value of these free parameters that are very, very huge. However, you can see that our predictions are quite sharp. So for example, in this case, you can see it's quite difficult to reach for the 100% of fuzzy dark matter. It's difficult to reach 10 to the minus 22 electron volt. So it stays around, let's say, 10 to the minus 20. And as you can see, for the decay constant, instead, we get a quite sharp prediction because we see that the decay constant can vary only of a 0.2 value. So it's a quite sharp prediction from string theory. Then we also consider another parameterization of the volume, which is a fiber Calabi-Yau, where we have two moduli this time, and therefore two axions, two ultralight axions, and here are the masses. And in this case, what we get is, again, the fact that it's rather difficult to reach 10 to the minus 22 electron volt, but you can get 10 to the minus 20 electron volt if you want 100% of that matter. And here we are plotting both the axions, where we have a isotropic parameterization of the volume, because if we slightly tune these coefficients, then we can see that only one axion of the two can make up fuzzy dark matter, while the other stays basically massless. And again, in this plot, we can see that the two decay constants should have rather sharp numbers of the decay constant. So around, again, 10 to the 16 GeV, but the variation is really, really narrow. So what we conclude from our study of C4 axions. So first of all, the assumption to make our study is the fact that we take a standard value for the initial value of the field. And but in our paper, we will study also some tuned scenarios. And as I told you, we take a very huge parameter, very huge range for these parameters, but however, the prediction are quite precise, and we ignore self-interaction. And what we see is that it's difficult to reach 10 to the minus 22 electron volt, and to have very light axion, you should have very small volumes, small in terms of the large volume scenario. The Kaluza-Klein scale in this case is quite high, so it's not a problem. And something interesting that we see is that if we take a multiple fuzzy dark matter model, we have that the heavier axion give a higher, is more represented than the lighter. And this is opposite to what astrophysics modeled. So it would be nice to see if it's possible also to get this scenario. Then we studied the proxion, which are axion giving this warped throat of the Calabi-Yau, which is here. And it was studied quite recently, as you can see. So the traction is basically an integral of a C2 of this two cycle that is shrinking when you go down the warped throat. And here, this time, we have a dependence on this M, capital M, which is the flux number. And here, most importantly, the mass is double suppressed with respect to the action. So it looks like a very promising candidate to be very, very light. And in fact, what we get is a bigger range of masses that this traction can have. And however, it's quite sensitive to the value of the string coupling. And the same goes for the decay constant, which have a bigger range. Yes. And again, it's sensitive to the string coupling. So it represents a very viable fuzzy dark matter candidate, and is the first time that the phenomenology of this particular axion is studied. So the assumption in this case, all these plots are for a fixed value of n equal to 10, and this is due to the fact that we have this assumption on the hierarchy among the flux numbers, because this is because we want to suppress the short wavelet instanton, and we want the attraction to actually dominate our potential. And so this implies to use, this implies that we are actually satisfying a mild version of the regularity conjecture. And the main outcome of the plot that I showed you is the fact that we can actually reach a mass of 10 to the minus 22 electron volt, but this time with the bigger volume of the Calabi-Yau. Then another thing that is under study is the fact that this time we have work replicating modes, and they are like very, so let's say borderline with the experiments. But the very, very interesting thing is that all these predictions are not spoiled when introduced also the Keller moduli, this setup. And this is a work in progress that I'm doing with Federico Carta, Alessandro Minimo, and Alexander Vespa. And this in turn means that even if we want then to stabilize all the moduli in the bulk of Yao, we can choose what we prefer. Would it be IWS or KKFT, and the prediction that I showed you will not be spoiled by this choice. So then something that we also derived are the inflationary scale and the tensor to scalar ratio for the C4 axion case and the traction. This comes from experimental constraints on the isocurvature perturbation. And so we had that the inflationary scale should be smaller for the C4 axion, actually quite low. And the tensor to scalar ratio is quite low, again, for the C4 axion, but it's really nice that for the traction can be pushed to a quite high level that can be actually detected by the next generation experiment. So it's really important to push the experiments to reach this value of R, because we will discover a lot of things. So to sum up what I showed you is we consider the string axion to be quasi-diametric candidates. And for C4 axion, we see that it's rather difficult to reach 10 to the minus 22 electron volts if you want 100% of quasi-dark matter. But the predictions in this case are independent of the microscopical tuning of the string theory parameters. And this gives also a low inflationary scale. So we have to live with 10 to the minus less than 10 to the minus 12 GeV as Hubble parameter during the inflationary epoch. While the traction appears to be independent on the compactification of the bulk of the Yao, so these predictions are quite general. And in this case, we can reach also 10 to the minus 22 in some cases. And we have a tensor to scalar ratio we can be possibly detected in the near future. So if you want more details, wait for our paper, which will come very soon. And I thank you very much.
Thank you very much for your nice talk. And now let's take questions from the audience. If you have any questions, you could just unmute and speak, or just raise hands. Either way.
I don't know. I feel
please
like a burden. Thanks for the talk. Can you explain a little bit why you have this in the traction case? The instantons are doubly suppressed. You have this e to the minus 2s.
Yes. This comes from the study of the 2019, and this is the fact that they are so usually. A normal work-taking mode in the throat is suppressed by a power of 3 of the work factor. But in this case, you can find that the traction is suppressed by powers of 6 of the work factor. So it's the suppression comes the work factor on the throat. And then we can write this in terms.
Is this what you mean by using the mild version of the weak gravity conjecture, or that's a different?
I use the mild version exactly because you can have both scenarios. Let's say when we have when we take the normal action and we multiply by the normal f, and then we get something that respects the weak gravity conjecture. But if we consider the effective decay constant of this axiom, which gets enhanced by this flux here, as you can see, the effective decay constant gets enhanced by the flux n, then we slightly violate the weak gravity conjecture.
Thank you.
Thank you.
Okay, any other questions from non-Pablo? Okay, I don't see any questions. So then let's thank Nicole again for the very nice talk.
Thank you
And then
very
let's move
much.
to the last speaker. So, Chiung, are you here? Oh, hi.
Yeah.
So could you start sharing your screen?
Sure. Sorry, 1 second.
Sure. Take your time.
Sorry, because recently I formatted my computer. So.
Oh, okay. Do you not see the share screen button?
Let me try again. Sorry. Oh, sorry about that. It seems I need to reconnect to Zoom. So let me come back soon.
Okay.
Yes, I'm very sorry about that. Yeah.
No problem, please. So I guess we will have maybe 1 or 2 minute break until he rejoins. So if anyone wants to discuss anything with the previous speakers, I guess you could speak up. Oh, Chiung has already joined, but still, you're welcome to speak for discussions while Chiung is preparing for his slides. Oh, already ready.
Slide? Yeah.
Yeah, we do see. Okay, sorry, we are not discussing now then. Okay, so Chiung is ready. So could you try actually turning to the next page if it works? Okay, it works. Great. Okay, so the last speaker of this session is Chiung Hwang from Cambridge, who will be telling us about E-strings on spheres. So please go ahead.
Thank you very much. And also I'd like to thank all the organizers for giving me this opportunity to present my recent work with Sarah Pasquetti, Shlomo Rosenman, Ebiata Sabak, and Matteo Sacchi. And today I'm going to talk about the E-string theory, 6D E-string theory, and its compactification, especially on spheres. So this is based on the following 3 works. And unfortunately, I won't have enough time to discuss all the details of the story. So instead, I'm going to focus on one particular phenomenon, which is very interesting, I think, and how we can understand it in terms of this E-string theory and its compactification. So let me first give you an example. So if we consider a very simple n=1 supersymmetric gauge theory in 4 dimensions, which is the SU2 theory with 8 fundamental chirals and 12 gauge singlet, which interact via this standard cubic superpotential, then we can set up this Q, we can define this Q and Q tilde in such a way that the SU8 symmetry of these 8 fundamental chirals into SU6 times SU2 times U1. In other words, here I define this Q as a SU6 fundamental and this Q tilde as a SU2 fundamental. Then the corresponding theory can be represented by this quiver diagram, where you can see 2 square nodes, which represent this SU6 times SU2 flavor symmetry, and SU2 gauge node in the middle. And you see 3 arrows, which corresponds to the bifundamental connect between 2 symmetry factors. They connect. And surprisingly, this very simple theory is known to exhibit a very non-trivial symmetry enhancement in DIR from this SU6, SU2 to U1 to the E6 times U1. And this is quite surprising because we didn't do anything very special or very complicated. We just take the SU2 theory with the 8 chirals and turn on some superpotential, which breaks the SU8 symmetry into this smaller SU6, SU2, U1 symmetry. However, suddenly we have an E6 times U1 symmetry in the IL, which is very surprising. And in addition, there is even a higher rank generalization of this model with the gauge group USP2Q instead of SU2, which looks like this. So we have a family of theories exhibiting this E6 enhancement. And the question is, why this happens? Why this simple theory has this kind of a special phenomenon? And can you have any deep understanding of this phenomenon in terms of anything we can study? So the answer is yes. So today I'm going to show you this theory is closely related to the E-string theory in 60. And you can, I will show you can obtain this theory as a compactification of the E-string on spheres. And then this 60 perspective will give you a natural explanation why we should expect this E6 enhancement from this simple SU2 theory. So good. So today I'm going to talk about this E-string theory and its compactification, which is a 60 CFT living on this M5 brains probing the M9 wall. Let's put this E-string theory on a tube or a sphere with two punctures. And we turn on the flux Ft of this SU2L times EA global symmetry of the E-string theory. And especially, it was shown that once you turn on these particular values of flux in this SO16 basis, then you will obtain a simple, not very simple, but you obtain a 4D n equal to 1 theory called FE USP2Q, which is coupled to the 16 fundamental chirals. So I will shortly explain what this FE theory is. But at the moment, you just remember that this theory preserves the two USP2Q symmetries. And then you can couple the A fundamental chirals to each USB vector in this way. So you naturally see the SUA symmetry which rotate those A fundamental chirals. However, actually, if you look into this flux more closely, this flux actually preserves not only this SUA symmetry, but also the E7 subgroup of the entire EA global symmetry of the E-string theory. So if this theory is indeed the compactification of the E-string with this flux, then we somehow expect that this theory should preserve the global symmetry, including E7, rather than just the SUA symmetry. And this is the case. For example, you can compute the superconformal index of this theory and see what the true global symmetry of the theory is in the IR fixed point. And once you do that, you can see that the theory actually preserves the symmetry E7 rather than the SUA using this superconformal index computation. So this, so next question is, what is this FE theory? So we have a Lagrangian description for this FE theory, which is given by this quiver diagram. So it looks very complicated, but you just remember a few things here. So for example, so you have a bunch of gauge nodes whose gauge ranks are increasing just one by one. So here, this is the dimension of the USP group. So the rank is 1 and 2, so it is increased by 1 at each step. And you also attach these 2 cube fibers only to the last node. And you also have a bunch of fundamental field attached to each gauge node. The thing is that I have said this theory preserves 2 USP factors. However, here you only see 1 USP2Q and bunch of SU2 symmetries. Indeed, the manifest symmetry of the Lagrangian is just the USP2Q times SU2 to the Q times U1 squared. However, you can, again, for example, using the superconformal index, this symmetry is enhanced to the USP2Q squared, and you will have this 2 non-trivial symmetry, which will play a very crucial role in our story. So you can also construct some gauge invariant operators. For example, you can construct a C in this way. So it's a collection of the bifundamental operator between each pair of SU2 symmetries. And as I said, those SU2 symmetries are combined and enhanced into the USP symmetry. So this C actually fits in the anti-symmetric representation of this enhanced USP symmetry. Also, you have this operator pi, which is in the representation, bifundamental representation between the 2 USP vectors. And lastly, you have another operator in the anti-symmetric representation of manifest USP symmetry. More interestingly, this theory is known to have a very interesting self-duality, which exchanges those two USP vectors. In other words, under this duality, you expect that this C and OH are exchanged because they are charged on each USB vectors, whereas this pi is mapped to itself under this duality. And this is one good way to see, one simple way to see those SU2 should be enhanced to the USB2Q, because only in that case, this USB2Q can be enhanced USB2Q can be exchanged with the manifest USB2Q. So in this way, you can see that you can expect that the bunch of SU2 vectors should be enhanced to the USB2Q symmetry. So this is the definition of the FE theory, but you can consider more general case, which looks like this. So you can have a more general gauge ranks, and you have a more general numbers of flavors. And this theory, this general theory, can be obtained from the original theory just by turning on some BAV to the OH and mass to the C. And those mass and BAV can be labeled by two integer partitions, rho and sigma. So once you pick up this rho and sigma, the gauge ranks and the number of flavors are determined by this equation. And once you pick this, once you choose this rho and sigma, the global symmetry is also broken to its subgroup, which is determined by this choice of rho and sigma. And the self-duality of the original FE theory, which exchanges those two USB vectors, now corresponds to the exchange of the rho and sigma. Therefore, in this way, you have a new 4D duality, which relate the two different theories in this general form. Interesting thing is, the important thing is that this new 4D duality is very alike the 3D mirror symmetry. So in our paper, we call this duality as a 4D mirror-like duality. And indeed, this new duality shares many aspects of 3D mirror symmetry, which is realized in 4D. So this is a FE low sigma family, which is placed a very crucial role in constructing the sphere model in the next part of the talk. So now we have an OR ingredient. So you can construct a sphere either by closing punctures or gluing in this way, or gluing the caps and tube in this way. So in either case, you need a cap theory, which can be obtained by breaking this USB puncture symmetry completely. But I have just explained how we can do that. So I explained how we break this USB2Q systematically. So for example, we first turn on the BAV of OH corresponding to this choice of sigma equal to Q, which breaks the puncture symmetries into SU times USB2Q. But we still have an SU2 vector here. So we want to break this SU2 as well. So we give a BAV to this M, which is the extra fundamental field attached to this broken puncture symmetry. Then by turning on this BAV of M, we can completely break this puncture symmetry, and we can obtain a theory sitting on this cap. And what is the resulting theory? The answer looks like this. So I won't explain the detailed computation here, but if you believe in me, you can just do the procedure I just explained, and then you can obtain this cap theory from this Bayesian tube. And now we have a cap theory, so you can now also close the remaining puncture, or you can combine two caps together to form the sphere. In the latter case, you have to specify how to glue the punctures. For example, since you have two copies of USB2Q puncture symmetry, you need to specify how you will identify those two USB2Q puncture symmetry and their charged field. For example, let's imagine the situation where you want to glue those two theories. Then you need to determine how you couple this M and M prime. So for example, there are two ways of gluing those those two theories, either using phi gluing or S gluing. So once you decide to use phi gluing, you can couple this M and M prime to a new field phi and turn on this superpotential. And therefore, in that case, those two M and M prime will be identified once you integrate out this phi field. On the other hand, if you turn on this, if you use this S-gluing, you turn on this mass term for M and M prime, such that they become massive in the IL. So you have two different ways of gluing the caps or tubes. And the resulting theory corresponds to two different fluxes, of course. One is determined as the addition of two fluxes, and the other is determined as a subtraction between them. So in this way, you can combine two caps and tubes. And let me give you an example. So let us glue two basic caps by S-gluing L1 and 2, where this L is the extra fundamental attached to the remaining puncture. And we use the phi gluing for the rest. Then following this rule, we expect that the resulting theory corresponds to the flux, the following flux. And the theory you obtain, since you turn on use the S-gluing for L1 and 2, you couple L1 and 2 to the L prime 1, 2, such that they become massive, and you use the phi gluing for others so that the two different sets of operators will be identified. Then the resulting theory will be the USP theory, USP2Q theory with the 8 fundamental and 1 anti-symmetric chiars, and the 16Q extra gauge singlet. And this theory, if you look at this theory, just the preserved symmetry is just SU6 times SU3, SU2, and U1 squared. And those matters are organized in the representation, the following representation. But if you look at this part, you immediately see that those matters can be represented in this way. And this is exactly the theory I showed you in the introduction. And this theory is supposed to exhibit the E6 enhancement. And we can now explain why we expect this E6 enhancement from this picture. Because we obtained this theory from the E-string theory compactified on a sphere with this flux. It turns out that this flux preserves not only the SU6 times SU2 times U1B in the E8 global symmetry, but the E6 times SU2 times U1 out of the E8 global symmetry of the string. So in this picture, it is very natural to expect that this simple as USP2Q theory, or if you take the Q equal to 1, this simple SU2 theory should exhibit the E6 enhancement, although it's Lagrangian only preserved the very simple subgroup SU6 times SU2, and etc. So in this way, I have, So far, I have explained how we can understand this surprising E6 symmetry enhancement of a simple 4D SU2 theory from the 6th perspective. And this is only a particular example, and there are more other interesting examples using different ways of gluing. For example, you can imagine a situation where the same E8 flux can be written in different ways in the SO16 basis, which then leads to different looking 4D theory, because the Lagrangian description I explained depend on this SO16 flux. However, those two theories should flow to the same IR fixed point, because although the fluxes are written in different ways in SO16 basis, they are actually the same E8 flux. So they comes from the same 60 theory compactified on a sphere with the same flux. So two different theories should flow to the same IR fixed points. So this explains the 6D origin of a 4D duality. And in our paper, we also give an explicit example realizing this phenomenon. Also, I need to mention there is an extra SU2 symmetry not descending from the symmetry of the E string in the previous slide. For example, this part descends from the global symmetry of the E string, but we have an extra SU2, which doesn't appear in the 60. And we were able to identify this SU2 symmetry as the SU2 isometry of the sphere where we compactify the theory. So actually this SU2 symmetry, or more precisely its U1 part is preserved by the tube theories as well, but used to be overlooked because it becomes anomalous when tubes are glued to form a torus. On the other hand, our sphere models are concrete examples which realize this isometric symmetry of the compactifying space in the field theory description. And there are many more interesting discussions related to this compactification of E-string, but today it's good to stop here, I think. So thank you very much for your attention.
Thank you very much for the very nice talk, Chiung. So question time. Are there questions? Okay, if there is no question from the audience, I have a very quick question, maybe a small question. So yeah, is it clear that the compactification of E-string theory on a sphere with arbitrary flux will lead to some non-trivial IR fixed point in 4D?
That's a very good question. It's not guaranteed. For example, so let me go back to the slide. So in this example, I used the S gluing for the two components of the fundamental and the Y gluing for the others. On the other hand, you can also use the S gluing for 4 component and Y gluing for the rest. In this case, you can still write down this theory, which is just the SU2 theory with 6 chiters. And you can also do the same. You can also use the S gluing more, then which will lead you the theory with the less flavor. And in that case, we know that the theory doesn't flow to the fixed point. It has no Suji vector. So this construction doesn't guarantee some IR interacting IR fixed point, but this construction can tell you that once you put the E-string theory on a sphere with some particular flux, then the resulting theory is just a theory without any Suji vector or interacting fixed point. Then you can say that this E-string compactified on this way will not flow to the interacting IR fixed point.
So it's not classified like for which fluxes it will work and for which it won't?
Yeah, it's not clear. Yeah.
Okay. Okay. If there are no more questions from the audience, then let's thank Chiung once again for the nice talk, as well as all the speakers of this session for their contributions. So thank you very much to everyone. And the last plenary session will be coming up in about 30 minutes, I think. So that will happen in the other Zoom session. So we will meet there again soon. Thank you very much.
Thank you.
Thank you.